All right, so welcome to 4.4. We're going to learn what a scatter plot is, and we're going to use those to write linear functions. It doesn't say linear, but they are linear today. All right, so let's write a function in function notation for this situation. It says the boat costs $4 per hour with a $16 deposit. All right, so we're using cost here, so let's use C, and it's H per hour, so C of H, right, equals $4 per hour plus 16, right? We start it, so the y-intercept is 0, 16, and we're going up $4 per hour. So 0, 16 is our first point, then 4 times 1 plus 16 is 20, and 4 times 2 is 8, plus 16 is 24, and 4 times 2 plus 16, 28. We're going up by 4s here, right? Because we're going up $4 per hour. So for each hour, we're going up 4. All right, these go 2, 4, 6. So 2 boxes up. The slope looks like it's 2, but the slope is actually 4, right? And so there is our linear function. We're basically going to be doing the exact same thing today, but we're going to be doing it for something called a scatter plot. So we've learned a bunch of situations like renting a boat, which follow a linear function pattern. But what about scientists? What about scientists who go and ask people questions and collect data? So here's a little scatter plot that it's called. So you hopefully see a scattering of black dots there, hence the name. And we asked a bunch of students, so each of these black dots is a student, okay? And we asked them, hey, how many minutes did you study for the test? And this one studied a little more than 30 minutes, and they got, looks like less than a 50, 40 something on the test. Now we don't know if it's out of 100 or not. If it's out of 100, these students didn't do so well. So because, right, this student studied almost 40 minutes and they still got an 80 something. But this person down here studied, what, like 9 minutes it looks like, and they got less than a 20, maybe a 10. All right. So this data hopefully is showing us that if you study more, you get higher test scores, right? That's why it follows a trend, right? We get higher scores over here when we have higher minutes studied over here. And it's roughly following a linear pattern. I've drawn a red line through those dots to sort of highlight the fact that those dots aren't just a random blob. There is a pattern there. That's not a perfect pattern. We know people who study lots for tests and that still do horrible. And we know people who study very little and still get A's. So here's our first scatter plot, okay? So you're taking these notes and pausing the video while you do that because I'm just going to start talking. So this next graph is about pool usage. That's where the title of the graph is, pool usage. And what is that about? Well, each of these dots is a day. And so we recorded the temperature on that day, and then we asked a whole bunch of people, did you go to the pool today? And then we got a percent for how many percent of the people we asked went to the pool, right? And on this day, the temperature was around 50, almost 60 degrees, and a little more than 20% of the people went to the pool. On these very cold days, and it doesn't say Fahrenheit or Celsius, but on these very cold days, a lower percentage, maybe 10%, right, went to the pool, right? Now, hopefully we realize when it gets hotter, more people, not everyone, more people go to the pool. So a higher percent go to the pool. Even though when it's really cold, there are people who still go to the pool. They're lap swimmers or they have indoor pools. Okay, and so we collected some data. And we got a bunch of dots. And a scientist wants to make sense of that data. They want to get a pattern from that data. And in some cases, the data suggests that it's following a linear pattern, a straight line. And so they want to draw a line that is approximately following the pattern. So how do you do that? So what I want you to do so that more of us get the same line, which was not going to happen, I want everyone to start at 10% there. So we're going to assume that when it's 0 degrees out, about 10% of the people go to the pool. Now, you're going to draw a line through this data. Now, You have to be smart about drawing your lines in your homework and in class today, because you want to be able to easily calculate the slope. So that means you want to look for lines that have good intersections. Now, so let's say I do, oh, well, the easiest, Mr. Ben, the easiest slope is 1, so I'll do that. Okay, so there's a slope of 1, and I drew that line. Well, that's not good. Why is that not good? Because look at all the dots. The dots are not near the line. They start near the line, but they're all, the line's too high. The dots are all below it. So let me get a smaller slope. Let's draw a slope of 1/2 maybe. Maybe that'll be good. Let's see. So let's see. 1/2's looking pretty good. All right, so 1/2 is looking pretty good. But, you know, we want to do as good as we can. You might want to try 1/3. See if 1/3 is. Now 1/3, let's look at 1/3. 1/3 looks a little too low. I was very sloppy on my 1/3, but that's approximately 1/3. See, with the slope of 1/3, more of the dots are above it. So I think I'm going to go with a slope of 1/2. All right, so that's where I'm going to do mine. So you'll notice, right, there are the good intersections. My line has a slope of 1/2. Is it perfect? No. I think there are a few more dots, maybe 1 or 2 below the line than above it. But of the easy choices, and I want to choose easy choices for my homework, I'm going to go with the slope of 1/2. Okay. So now I'm going to write a function for this, right? So we're going to use P for percent of pole usage. We're going to use T not for time, but temperature. And we're going to say that P of T equals 1/2 the temperature. We take whatever the temperature is and multiply it by 1/2. Yeah, that's the rate. Here goes the slope. Oh, I got to make sure. Oh, I said it was 1/2, but I got to make sure that these actually come out as 1/2. Yeah, I'm lucky. I should have checked this first. Is that right? Although this is not 1/2, it's 5/10. It's simplified to 1/2. Okay. So it's 1/2 t, and then what was the y-intercept? Well, it was 10%. And that's a linear function that represents people going to the pool, right? So you could use this equation in the future to predict, at least for this group of people, hey, the temperature is 100 degrees. If the temperature is 100 degrees, what percentage of the people of this group will go to the pool if it's that hot? Well, it says, from the graph, it says when the temperature is 100 degrees, 60% of the people will go to the pool. Let's see the math here, right? 1/2 of 100 degrees is 50, and 50 plus 10 is 60. We'd get 60% of the people going to the pool, right? What if it was 60 degrees? What percent would go to the pool? Well, it seems to say that when it's 60 degrees out, that 1/2 of 60 is 30, plus 10 is 40. 40% of the people will go to the pool. And so we have a model for that. Now, do we actually have any day where it was 60 degrees and 40% of the people went to the pool? No, we don't. We don't have any day that says that. Okay? But the model, this is a model or an approximation of this data, says that's a good, reasonable guess, right? Higher guesses are certainly going to be too high most of the time, because if you guess up here, right, that's way too high. Or if you have your model down there, your guesses will always be seemingly too low. Okay, so let's try this again. This is called drawing a line of best fit. That's the red line we drew for a scatter plot. The dots are the scatter plot. All right, so here's another one. Now this time, each of these dots is a plant. And we took different plants. It's not all the same plant. And we said after this many days, which is almost 80 days, how many inches tall was this plant? That was the same type of plant. And then this day, like 35 days, this plant was this tall. Now, I think this is less looking like a straight line than the last one, but there's a general linear pattern here. Now, to make everyone have more likely to have the same answer, I want you to begin this at 5 inches, right? That's where 5 inches, because it's going 5, 10, 15, 20 there. That's where 5 inches is. So we're going to write a linear function, h for height is a function of days, blank days, and we know we're all going to start at 5 inches. Right? So we're saying when we put this plant, when we put it in the ground, it was 5 inches, right? Because it says that. The height of several plants that began at a height of 5 inches. So they all began at 5 inches. But if you give a plant, 2 plants, the same exact water, the same exact sunlight, they're not going to grow exactly the same, okay? But hopefully we realize, unless they die, plants will continue to grow as long as you give them sun and water. Okay, so now we're going to draw our linear function. Once again, we're going to try to pick a slope that makes our life easy. So let's try 1/2 again. Wasn't that the last one? Yeah. So let's look at 1/2 again. Yeah, this time 1/2 looks a little high, right? Because too many dots are above it. So try to pick something other than 1/2. All right, I picked 1/3, it looks like. Yeah, remember this is 5 and this is 15, but it does simplify to 1/3. Could someone reasonably say, I think 1/4 is better? Yeah, you could. Let's look at 1/4 just to compare the two. All right, and 1/4, I think 1/4 is not as good. It has too many dots above it, but it's a reasonable one. If you put that in the homework, I would not be upset. So we're going to use 1/3, h equals 1/3 d plus 50. All right, so let's test our model. So we're going to do h of 50. We're going to see what the model says at day 50. That's right here. Right? It says something a little above 20, right? That how tall a typical plant would be. So h of 50 would be 1/3 times 50 plus 5. Well, unfortunately, 3 doesn't go into 50 perfectly, but 3 into 20, so it's going to be 18 2/3 or 18.6 repeating. And so we're going to get approximately, it's approximately what, 23 2/3, or you could say approximately 23 inches. Right, and that's what that is right there. Is there any actual plant that does that? But that's what the data predicts. That's what you use this for. You collect some data and then you make predictions about what will happen next time. Okay, so now when you're drawing your line of best fit, you may have one point that is way off to the side. My advice, this is something scientists argue about, but my advice, you ignore your outliers, is called. So let's look at this one. This is a graph where we asked a bunch of couples the age of the husband and the age of the wife. So right there, this is, the wife is 90 years old. I think that's 90 years old. And the husband here was, I think these are going up by 5, 85 years old. All right, he was a little younger. And here, right, the wife was 20 and the husband was 20. Okay, but there is an outlier here. So I want everyone to circle the outlier, the one that does not fit the pattern. All right, hopefully you're circling that, because that's sort of icky, right? Because we've got a husband who's 80 years old and we got a wife who's only 20. All right, they're 60 years apart. That doesn't happen very often, yes. And so when you don't want to make a prediction based on these people, right? They're very unusual, let's put it that way. So I'd like you to start this one at 0, 0, okay? And then try to find a slope that's going to be easy for this graph. Well, I came up with that, and I think I didn't, let's see, I didn't really draw it very well. I think I meant to do a slope of 1 here, I did, but I didn't draw it very well. So I came up with a slope of 1. And so, right, so we'll use h for husband and as a function of wife, because you always use the y-axis there as the output or the dependent variable. And we're going to use a slope of 1. So h of w equals w. That's as simple as I can get it, right? The husband and wife, right, are approximately the same age. Probably in the real world, if I did this, you'd probably add 1 or 2 years to it, but I was keeping it simple. So let's see what this says. It says the wife is 60 years old, H, right? If the wife is 60 years old, what do we expect the husband to be? We expect them to be 60 years old too, right? And there's one that's almost that right there, all right? If the wife is 60, we expect the husband to be 60. But the point of this graph is you have some weird data point. That doesn't ruin your data. You don't shift the whole line over here just because of that. No, because you want to make a line that predicts the future for the typical situation. Okay. All right. So now we're going to draw a line of best fit this time, but this is going to have a negative slope. So take these notes, pause, take the notes, and then I'll talk more. So the following data was collected about the height of several candles that began at a height of 18 inches. So they all began at 18, right? So we're going to write this linear function. It's going to be plus 18, and it's going to be the height as a function of time. Okay. So now we need to fill in the slope here, right? We're going to find the slope here. So these were different candles that were all 18 inches. And if you light a bunch of candles, you took a bunch of candles in a science class and all lit them at the same time, depending on the wax and the wind and the temperature in the room, they will all burn not exactly the same. And so we took a bunch of measurements at different times. Okay, so let's try to draw a line of best fit for this data. Now, you can't draw it like that. Yeah, half the dots are above and half the dots are below, but it's not following the pattern. The pattern of the data, the line is going this way. Yeah, we have an outlier here, so we're going to ignore that. And maybe this one's an outlier too. But right, generally all the rest of them are following a pattern, right, that goes down, right? This is a candle burning down. So I'm going to draw this line. You draw your line and then wait and see mine. So we circled the outlier, I did that. And there's the one I drew. So let's find the slope of that. So down 2 and over 1. This one's going down 2 and over 1. Now, this is 1, 2, 3, 4. Yeah, so each box is worth 1. So it's down 2 and over 1. It's a -2 slope, right? Please. This is a negative situation. We're going down. So you have to use your common sense. Candles do not burn up. So having anything that went up is ridiculous. But also that doesn't follow the pattern. It has to follow the pattern of the dots. All right. So we're going to find H at 6 hours. So it's -2 times 6 plus 18, -12 plus 18. H of 6 is it 18? Is 6. Okay. So at 6 hours, let me clean up the data here a little bit. At 6 hours, we would expect, oh, it's right, that red mark is what the prediction is. At 6 hours, we predict the candle will be 6 inches tall. Was there any candle that did that? No, none exactly. All right, but there were several that were close. All right, please take these notes. So in this graph, we asked a bunch of people how many hours they slept last night. And then we asked them if they went to the pool. Now, we clearly showed that, at least according to the previous graph, several graphs ago, that when it gets hotter out, more people go to the pool. But what about sleep? If you sleep a lot, do you more likely go to the pool? Or maybe you miss the pool? No, that doesn't seem to make a lot of sense for most people, right? Do you get up early? Do you go to the pool? No, those things don't really have anything to do with each other. And when scientists do this happens to them. They have these ideas that maybe people's going to pools has something to do with how they sleep. And they'll go and collect data and they get patterns like this. This is nonsense. Do not write a line of any kind in this, right? This has no pattern, right? You could draw something like that, and yeah, half the dots are above it, half the dots are below it. You could even draw like that. Half the dots are above it, but there's no pattern. They're not, these dots are not clustered along a line. They're just random. So you just, right? You do not draw a line of best fit if the pattern is not linear. The pattern here is not linear. All right. So that's what I just said in the notes. We should not write linear functions, which are straight lines, for nonlinear data. So in this one, we took temperature, not against people going to the pool, but whether they turn their air conditioner on. Let's think about what happens with air conditioners. It's different than pools, right? When it's cold out, this drops to 0, right? Only weird people would be turning on their air conditioner when it's already cold out. So at all these temperatures, we're getting 0%, 0%, 0%, 0%. Then it starts to get hot, and everyone starts at the same time, starts turning on their air conditioner, right? Some of you people will start turning on the air conditioner at 60, at 60 degrees, which seems a little soon, right? But by the time it's near 100 degrees, like a lot of people almost everyone has turned on their air conditioner. So, you could try and draw a straight line, but this pattern, but right now these are not following that straight line. Okay, and we're always going to start our line over there. All right, so this data is a poor fit because it's not linear. That's the line that fits this data, and it's not straight. Linear means straight line. All right. So this time you're going to have to make these dots yourself if you were doing this in class. So 0, 0 would go right there. 1, 4 would go right there. That's 4. 1, 6 would go there. 2, 10 goes there. Right? I'm just taking these points and putting on. This is what scientists do. They collect a bunch of data and then they put the points on there. Once you've done that, you're going to draw a linear function through there. And we're going to try to have a good slope that makes our life easy. And that's what I came up with. And here's where we have to be careful. I put one of these in here. Good for me. 1, 2, 3. All right, so this one here is 1. The rise is not 3. It's 3 boxes, but we got 2, 4, 6. The rise is 6. So the slope here is 6. When we get to the test, if I put one like that, I will get wrong answers from some of you for sure. So the slope here is 6. We're doing height as a function of time. And we get, so 6t, and the y-intercept was 0. So h of t equals 6t. The following data was collected about the height of water in several tanks that began to leak at a height of 13 inches. All right, so you're supposed to start your line at 13. Use the data to write a function using a line of best fit. All right, so we're going to do h of t, and it says blank times t plus 13. So what slope are we going to pick that follows this data? All right, I picked that. What slope does that have? Well, let's make sure. We got 1, 2, 3, 4. Yeah, I went back to it nice and easy. So we're going down 1 over 2, down 1 over 2. Hopefully everyone is doing a slope of negative 1/2, right? Because we're going down 1 over 2. The water level is dropping in this tank. It's getting lower and lower. The only way we're going to be able to do that is with this negative slope. What do we expect the water level to be at 17 hours? Okay, well there's 17 and there's the answer. So that looks like 5. Let's see if that works out. Negative 1/2. I don't think it is 5. I think it's close to 5. Negative 1/2 times 17 plus 13. Okay, well half of 16, right? Half of 16 is 8. Half of negative 16 is negative 8. So this is negative 8.5, let's say, and plus 13. Well, that is not, right? That is x13 minus 8.5 is, in fact, 4.5. So this is negative 4.5 inches. So it looked, that's one of the dangers of reading off a graph. That looked like 5. It really did, all right? But the truth is the math says it's negative. Whoops, what happened here? I definitely made some mistake here. Oh, positive 4.5 inches. That's why. Because it says negative, that would be down below the graph. Positive 4.5 inches. All right, final question. So this is true. When you buy a car, all right, and we're not talking classic car, a regular car, the value of that car drops very quickly when you drive off the lot. If you drive off the lot, unless they have, some dealers have a return policy, but then you went, say the next day you wanted to sell the car, 1 day later, you'd lose thousands of dollars. Yeah. So unless they have a return policy, which some dealers will let you return it in 24 hours. Tesla used to, but they don't anymore. And it's not going to follow a straight line. It drops a lot right away. And so it curves like that and sort of levels off. And so why wouldn't you, so this, if appropriate, use the data to write a function using a line of best fit. Not appropriate. So don't write a linear function for this. This is non-linear data. All right, thank you.